Hello students, welcome to EPG Pathshala. I'm Dr. Anjali Sharma from University of Delhi. Today we are going to discuss about the module Life Cycle Analysis from paper Energy Related Materials. So students, let us see what we are going to learn in this module. From this module, we may get to know about the following things. First, what is life cycle analysis? Second, what methodology is adopted for life cycle analysis? And third, contradiction associated with this technology. The concept of conducting a detailed examination of the life cycle of a product or a process is relatively recent one, which emerged in the response to increased environmental awareness on the parts of the general public, industry and governments. The immediate precursors of life cycle analysis and assessments that are also known as LCAs were the global modeling studies and energy audits of late 1960s and early 1970s. These attempted to assess the resource cost and environmental implication of different patterns of human behavior. LCAs were an obvious extension and became vital to support the development of eco-labeling schemes which are operating or planned in a number of countries around the world. In order for eco-labels to be granted to chosen product, the awarding authority needs to be able to evaluate the manufacturing process involved, the energy consumption in manufacture and use, and the amount and type of waste generated. To accurately assess the burdens placed on the environment by the manufacture of an item, the following of a procedure or the use of a certain process, two main stages are involved. The first stage is the collection of data, and the second stage is the interpretation of that data. A number of different terms have been coined to describe the processes. One of the first terms used was life cycle analysis, but more recently two terms have come to largely replace that one. That are first life cycle inventory and second life cycle assessment. These better reflect the different stages of the process. Other terms such as cradle to grave analysis, eco balancing, and materials flow analysis are also used. Whichever name is used to describe it, LCA is still a potentially powerful tool which can assist regulators to formulate environmental legislation, help manufacturers analysis their process and improve their product, and perhaps enable consumers to make more informed choices. Like most tools, it must be correctly used, however. A tendency of LCAs is to be used to prove the superiority of one product over the another, which has brought the concept into disrupt in some areas. An effective LCA allows us to calculate a product's environmental impact, identify the positive or negative environmental impact of a process or product, find opportunities for product and product improvement, to compare and analyze several processes based on their environmental impacts, and also to quantitatively justify a change in a process or product. The LCA method provides researchers or companies with quantitative data for their current products. By looking at a product's life from the raw material extraction to its disposal, the environmental impact of each process and material can be analyzed. The LCA allows us to determine and analyze the technology, economical, environmental, and social aspects of a product or process necessary to manage the complete life cycle. With this quantitative data, the desired changes can be justified with respect to the cost and environmental impacts of a product or process. Life cycle Assessment is a process to evaluate the environmental burdens associated with a product, process, or activity by identifying and quantifying energy and materials used or waste released to the environment. To assess the impact of those energies and materials used, the releases to the environmental, and to identify and evaluate opportunities to affect environmental improvements. The assessment includes the entire life cycle of the product, process, or activity, encompassing extracting and processing raw materials, manufacturing, transportation and distribution, use, reuse, maintenance, cycling, recycling, and final disposal. Life cycle assessment has emerged as a valuable decision support tool for both policymakers and industry in assessing the cradle to grave impacts of a product or process. Three forces are driving this evolution. First, government regulations are moving in the direction of life cycle accountability. The notion that a manufacturer is responsible not only for direct production impacts but also for impacts associated with product inputs, use, transport, and disposal. Second, businesses participating in voluntary initiatives which contain LCA and product stewardship components. These include, for example, ISO 14000 and the Chemical Manufacturer Association's Responsible Care Program, both of which seek to foster continuous improvement through better environmental management systems. Third, environmental preferability has emerged as a criteria in both consumer markets and government procurement guidelines. Together, these developments have placed LCA in a central role as a tool for identifying cradle-to-grave impacts both of products and the materials from which they are made. The life cycle or cradle-to-grave impacts include the extraction of raw materials, the processing, manufacturing, and fabrication of the product, the transportation or distribution of the product to the consumer, the use of the product by the consumer, and the disposal or recovery of the product after its useful life. LCA started in early 1970s initially to investigate the energy requirements for different processes. Emissions and raw materials were added later. LCAs are considered to be most comprehensive approach to assessing environmental impact. What makes up LCA? There are four major linked components of LCA, including goal and scope definition. The basis and scope of the evaluation are defined in goal and scope definition. Second, inventory analysis, which create a process tree in which all processes from the raw material extraction through waste water treatment are mapped out of and connected, and mass and energy balances are closed, that is, all emissions and consumptions are accounted for. Third is impact assessment. Emissions and consumptions are translated into environmental effects. They are environmental effects which are grouped and weighed. These 3 points are interrelated to fourth point, which is interpretation of result, where areas for improvement are identified. Let us see all these 4 points in a broader spectrum. First, goal and scope definition. The goal of LCA is to compare the full range of environmental effects assignable to products and services by quantifying all inputs and outputs of material flows and assessing how these materials flows have an impact on the environment. This information is used to improve processes, support policy, and provide a sound basis for informed decisions. Let us see one example where we have goal to increase online sales of jewelry by 30% in 8 months. The scope for this would be open a storefront online, write a monthly blog posted on website about jewelry care. Third, to optimize the site content for better Google ranking. Inventory analysis. Inventory analysis or life cycle inventory analysis involves creating an inventory of flow from and to nature for a product system as shown in the figure given. Inventory flows include input of water, energy, and raw materials and releases to air, land, and water. Inventory flow quantifies the energy, water, and raw materials inputs and environmental releases to air, land, and water associated with each stage of production. The third major component of LCA is life cycle impact analysis or assessment. Inventory analysis is followed by impact assessment. This phase of LCA is aimed at evaluating the significance of potential environmental impacts based on the LCI flow results. Classical life cycle impact assessment consists of the following mandatory elements as shown in the schematic. So first is the LCIA inputs. These are the selection of impact categories, category indicators and characterization models. For example, chemical emissions to air, water and land. Also, resources. Second, midpoint categories. The classification stage where the inventory parameters are sorted and assigned to specific impact categories. For example, chemical emission to air, water and land leads to human toxicity, respiration effect, ionizing radiations, ozone layer depletion, photochemical oxidation. Also, aquatic ecotoxicity, terrestrial ecotoxicity, acidification, eutrophication, land use, climate change, mineral extraction of non-renewable energy, water abstraction. Third is endpoint category. These impact measurements where the categorized LCI flows are characterized using one of many possible LCIA methodologies into common equivalence units that are then summed to provide an overall impact category total, such as human health degradation, ecosystem quality, example loss of biodiversity, climate change, resource consumption, and water impacts. The last, fourth component of LCA includes interpretation. Life cycle interpretation is a systematic technique to identify, quantify, check, and evaluate information from the results of the life cycle inventory and or the life cycle impact assessment. The outcome of the interpretation phase is a set of conclusions and recommended for the study. According to ISO, the interpretation should include first, identification of significant issues based on the results of LCI and LCIA phases of an LCA. Second, evaluation of the study considering completeness, sensitivity and consistency checks. Third, conclusion, limitations and recommendations. For more details, let us see what is the methodology for life cycle assessment. A useful methodology for life cycle assessment follows these steps. First, research and develop an understanding of the supply chain from raw material production to end use. Second, sketch a supply chain showing important processes and primary mass and energy flows. For examples, processes include energy and chemical conversions, production, and transport of fuel and fuel storage. Mass flow include the flow of raw materials, fuels, waste product, and emission. Energy flows include the use of electric power, additional chemical energy consumed in a process, and work done on the process. Third, identifying the bottleneck processes which consume the largest amount of energy or produce the largest quantities of harmful emissions, or both. Fourth, analyze the energy and mass flow in the supply chain using a controlled volume analysis and the principles of conservation of mass and energy. A controlled volume is a volume of space into which and from which mass flows. The boundaries of the control volume are shown by a control surface. Draw a control surface around individual processes in the supply chain with particular focus on bottleneck processes. Analyze the mass and energy flow entering and exciting these processes. Employ the conservation of mass equation, that is m1 minus m2 gives delta m, where m1 is the mass entering the control volume, m2 is the mass leaving the control volume, and delta m is the mass accumulating within the control volume. Employ the conservation of energy equation for steady flow as given below. Q dot minus W dot is equals to M dot bracket M2 bracket H2 minus H1 plus G times Z2 minus Z1 plus half of V2 square minus V1 square with bracket closed, where Q dot is the heat flow into the process, W dot is the rate of work done by the process, M dot is the mass flow rate, H2 minus H1 is the change of enthalpy between outgoing and incoming streams, and G is the acceleration of gravity. Also, Z2 minus Z1 is the change in height, and V2 square minus V1 square is the change in square of the velocity. The last three terms refer to the change in internal energy, potential energy, and kinetic energy of a flowing stream respectively. Having analyzed the individual processes within the supply chain, evaluate the entire supply chain as a single control volume. Aggregate net energy and emission flows for the chain. Next, quantifying the environment impacts of these net flows, for example, in terms of human health impacts, external cost, and potential for global warming. Next, compare the net charge in energy flows, emissions, and environmental impacts of one supply chain with another. Next, rate the environmental performance of each supply chain against the others. Finally, repeat the analysis for an expanded, more detailed number of processes in the supply chain. There are few contradictions of LCA. Let us see what are these contradictions. Many LCAs have reached different and sometimes contradictory conclusions about similar products. Comparisons are rarely easy because of the different assumptions that are used. For example, in the case of food packaging, about the size and form of container, the production and distribution system used, and the forms and the type of energy assumed. To compare two items which are identically sized, identically distributed, and recycled at the same rate is relatively simple, but even that require assumptions to be made. For example, whether deliveries were made in a 9-ton truck or a larger one, whether it is used diesel or petrol, and ran on congested city center roads where fuel efficiencies are lower, or on country roads or motorways where fuel efficiencies might be better. Comparisons of products which are dissimilar in most respects can only be made by making even more judgments and assumptions. Preserving the confidentiality of commercially sensitive raw data without reducing the credibility of LCAs is also a major problem. Another is the understandable reluctance of companies to publish information about the product which may indicate that their own product is somehow inferior to that of a competitor's product. It is not surprising that many of the studies which are published and not simply used internally engross the views of the sponsors. So students, let us leave you with an exercise in the end and you think about these points. What is the function of LCA? What is the functional unit? What materials and resources are used? What does it take to produce both? What are the impacts to the environment? Is there any waste? Does washing the china produce waste? What type of data do you need? And how do you know which one is better? So students, let us summarize what we have learnt in this module. The four steps that comprise the life cycle assessment allow one to examine the full extent of environmental and economic effect assignable to products and processes in order to make more informed decisions. In today's manufacturing world, life cycle assessments are becoming increasingly complicated due to extensive globalization evidenced worldwide. Despite such difficulties, LCA is an invaluable tool when comparing the environment impacts of various products and processes. By performing life cycle analysis, manufacturers around the globe are able to quantitatively see the environmental impacts and associated money flow of their products and processes. Companies can make necessary corrections to decrease economic costs and, more importantly, decrease the environmental impacts and find better ways to make their products. So, now in the end, let us leave you with an exercise and you think about these points. What is the function of LCA? What is the functional unit? What materials and resources are used? What does it take to produce both? What are the impacts to the environment? Is there any waste left behind the LCA? Does washing the china waste products? What types of data do you need? And how do you know which is the better one? Thank you.